Hello, everyone. We are Team 2. Our team is made up of Kevin, Romney, Sanchit, and Siddharthan. Our research question is, how can a snake-inspired biodegradable robot be created using foldable robotics principles? For our animal, we decided to use a boa constrictor to use as our biomechanics-driven inspiration. The reason why we used a boa constrictor is because these animals use rectilinear locomotion. Rectilinear locomotion is when there are two opposing muscle groups. One muscle group lifts the snake vertically, while the other muscle group pulls the snake's scales backwards, which propels the snake forward. We are particularly interested in rectilinear locomotion because it's useful when navigating rough terrain. We also looked at bio-inspired snake robots that utilize rectilinear motion. With this robot made by Georgia Tech, we took some key takeaways from it. Those being, this robot shows vertical and forward motion, has a closed loop, and uses longitudinal wave. Additionally, using the boa constrictor as inspiration, we also took the parameters from this animal. From the parameters, we had the key takeaways of that the speed of this animal and our mechanism would be slow moving, and also that we would need to have a closed loop in order to overcome forward and backward sliding friction.
Here is our proposed mechanism for a snake-inspired biodegradable robot. The proposed mechanism is a 1 degree of freedom system designed to simulate a snake's rectilinear locomotion. It is made up by two sarrus linkages contracting and expanding opposingly. The mechanism will be driven by a motor held in the center of the robot actuating one of the interior sarrus linkage angles. The end effectors are to fold up and down to allow the robot to push and pull or slide when needed. The exact way these end effectors move and make contact with the ground is still subject to testing and changes. Below is the current physical prototype of the snake-inspired biodegradable robot. This prototype will be used to test whether the current design will be able to locomote similarly to a snake's rectilinear locomotion. This design features vertical motion, horizontal motion, and attempts to mimic the longitudinal waves present in rectilinear locomotion using its two links. Here are the kinematics for our first sarrus linkage. A 2D model was created using two 2-bar linkages AB and ED with a constant distance at the endpoints, creating one independent state QAI and three dependent states QBD, QDD, and QED. Constraints were then added to make the two vertical links parallel, and PFE and PDC have the same Y component. These simulate the constraints a 3D representation of the sarrus linkage would hold. Using this model, the internal and external Jacobians were calculated to map output velocities and forces to input velocities and torques to QAI. The force at the end effector was estimated using recorded mass and accelerations to estimate the ground reaction forces. This was then used with the external Jacobian to calculate the required input torque of 0.31 Newton meters. These kinematics are to be revised with the new design of the robot, but similar methods will be used to create the updated model. In the future, we plan on iterating upon the mechanism and performing rapid prototyping to determine the viability of various configurations of the proposed mechanism. We also plan on revising our kinematics with our increased complexity design. Following that, we will model dynamics for the proposed robot. There are still some questions that need to be answered to complete the robot. We still need to determine which materials we will be using for the construction of the body of the robot. This will likely be determined by a trade study based on weight, durability, stiffness, and time required to degrade. With this biodegradable material, we will then need to determine how our robot will be manufactured and what folding techniques will be used to construct the final robot. A motor also needs to be selected and purchased based on motor torque requirements of the new design. Lastly, some testing will need to be performed to determine whether the current end effector mechanism will be effective in allowing the robot to locomote similar to snake-like rectilinear locomotion. And here are the sources used in this presentation.